Hello, my name is Mark Gibson, and you're listening to the podcast version of the Teagasc Signpost series, a weekly webinar that promotes and examines sustainability in Irish farming. So today I'm delighted to be joined by Professor Donagh Berry, who is a Teagasc animal breeder and geneticist.
Yeah, so as you said, Mark, I'm a geneticist, so that means I work on animal breeding across many different species. Dairy, beef, sheep, doesn't really make a difference. It's all just numbers to the likes of us. I'm also a director of the VistaMilk SFI Research Centre, which is an agri-tech centre started around 2 years ago. So I'm based in Teagasc, down in Moore Park.
Very good. So you're going to be talking to us today about the cumulative and permanent strategy to environmental stewardship. So what does that mean?
Well, as a breeder, one of the real benefits of breeding is, as what you say, it's permanent and cumulative, which means is that the genes that you have in the cattle or the sheep of today is what you have introduced over the past few decades and centuries. And that's really important. So if we look at some strategies that you could do to, for example, improve animal health, vaccines, you'd have to vaccinate your animals every single year. While if you could breed for improved health, then you actually benefit on that every single year. And also it's kind of at no cost. Vaccination costs a bit of money, but you have to get the cow and calf, or you must get the ewe and lamb. So you might as well do a good male animal as opposed to a bad male animal.
Right, that's a really, really good way of describing the benefits of it. So, okay, well, look, if you could share your screen with us and we'll get into your main presentation, and a reminder for everybody that you can ask questions at any stage, or if you want clarifications on any of the material that Donagh is presenting, please do feel free to get in touch with at any stage throughout this morning's session. So over to you, Donagh.
Yep, great. Thanks, Mark. So as you say, what I'm going to predominantly focus on, even though I'm talking about lowering Ireland's environmental footprint, I'm going to specifically focus on animal breeding. But those of you that are not in the animal breeding domain will probably be able to recognize some of the tools that we're using, or the vehicles that we have available to us that we could exploit for non-breeding purposes, okay? I just want to quickly start off, given the generality of the audience that we have, is what are these things called ruminants? And ruminants are animals that have a thing called a rumen. So most of these animals will have 4 stomachs, and it's in this rumen, which is kind of like a biodigester. It's where all the digestion of the grass and stuff like that happens. And in doing that, the microorganisms that digest that grass actually release this thing called methane. So it's an important point is that around 40% of the land area in the world is made up of grass. And I'm not sure if you've ever tried to eat a bit of grass, but you can't really eat grass. You can't digest it as humans because we don't have these 4 stomachs. We don't have this rumen. So that's the real advantage of these ruminants, is that they can digest this product, which is inedible to humans. And they can convert that then into energy and into protein. And that's really, really important. So they're essentially harvesting an energy source and transferring it to a different type of energy source, which of course we as humans can actually digest and get the nutritive value from that. I should also say that a lot of these grasslands cannot actually be used to produce much else. So it's a really efficient way of producing food. The second point I want to make, and I certainly am no expert in this, is what are greenhouse gases. So if you look at the graph there on the left-hand side, it's the greenhouse effect. Okay, it's just like you go into the greenhouse at home. It's a bit warmer than probably outside because the light or the sunlight is shining in through it, and it's being stopped from going right back up again. So that's the top of your glass house is stopping that radiation going back out. So from a greenhouse gas perspective, rather than having the top, which is glass, you just have these gases. And these gases on top of the world then stop they reduce the amount of radiation that gets increases and increases the temperature of the world. Should also be borne in mind that these are really important gases. If we didn't have them, we'd absolutely be freezing in the world. Okay? But the problem is that they are increasing globally. And there are many different types of greenhouse gases. I'm just showing you here under the table on the right-hand side. Methane is the one we talk probably most about when we talk about agriculture. But there are other gases like nitrous oxide, for example, that are also produced from agriculture. On the far right, I'm showing this statistic, and this is coming under a bit of scrutiny at the moment, but I'm not going to go into the detail of that. It's called the global warming potential, or the GWP. What this essentially is what's the amount of carbon dioxide equivalent, which is another greenhouse gas. What is the amount of carbon dioxide equivalent that would heat the Earth to the same extent over, say, a 20-year period? So if we look at methane, for example, 84 to 64 there, you can see that has the equivalent around 84 to 60 or 86 times as potent as carbon dioxide. The other thing about methane to bear in mind compared to a lot of the other gases is that it doesn't last in our Earth or in our atmosphere as long. You know, its lifetime is only around 10 to 12 years. So it does reduce. But again, I'm not going to go into the details, and we can argue for days and days about the cycle of methane going into the soil, etc. But what we know is that methane is a greenhouse gas, and that is contributing to global warming. So have we strategies available to us that could potentially reduce the amount of methane, but also a lot of the other greenhouse gases, and also a lot of the other environmental impacts, like the nitrates, the nitrogen going down to the ground and into our groundwater. These are all intrinsically linked. And to do that, and we're getting a little bit technical, but let's take our time going through this. You may have already heard about this marginal abatement cost curve. Abatement is just really a fancy word for reducing. So can we reduce the environmental footprint of agriculture, and what are the toolkits available to us to do that? So what I'm showing you here is, this is as I said, the marginal abatement curve produced by Gary Lanigan from Teagasc and his colleagues. On the vertical axis is what we call the cost benefit. So anything that is above that line of zero, that is costing the farmer money. So if it's a tool, like for example, fertilizer type there, you can see that's costing, it's above the line, so it's costing the farmer a bit of money to implement that technology. Anything below this line is free. In fact, the farmers actually make money if they adopt this technology. So that's the first point to take from this map. Anything above this line costs money. Anything below this line, producers can make money by implementing it. The second point to take from this curve, or this graph, is the width of the bar. And that is the abatement potential, or as I said, abatement is just a fancy word for reduction potential. So the width of the bar will tell you how good is this technology at reducing the environmental footprint. Okay. And I just want to focus on one of them because, of course, I'm an animal breeder. There are two things that are really available to us from a beef and a dairy perspective. It's the beef genomic scheme here, and I'll talk about this in later on. It's an index or a tool that we have available to us that ranks animals based on their expected profitability. So 2 points to take from it. One, it's below the line. Both of them are below the line, which means that if the farmers adopt this technology, they will make more money. It's good for the environment and they will make more money. Secondly is look at the width of the bar, especially if the dairy one, really wide bar, which means that it has a huge potential to reduce the environmental footprint. So it's win-win. Reduce the environmental footprint dramatically, the farmers make money. And the important point, and this is what I said to Mark at the start, was it's cumulative and permanent. So this is up to 2030, but at 2030, if you stop breeding, you still can exploit that benefit. Fertilizer type, for example, you have to keep spreading that fertilizer, and if you stop, then you go back to the status quo. You don't do that from the breeding perspective. Another real important point, and this is a negativity associated with this attribute of breeding, is that if you're breeding for the wrong thing, then you're breeding in the wrong direction and getting worse and worse with every generation. So there's 2 points we need to be cognizant of here. We need to recognize what is our current breeding strategies doing for environmental footprint. And if they are going in the wrong direction, then we need to address that. And essentially, that's what my talk is about. But before I go any further, because I would have gone to college and people would have said, breeding is slow and it'll take ages and you won't make much improvement. It's completely untrue. This is the Guinness Book of Records. This is the cow holding the Guinness Book of Records for the most amount of milk she can produce. She produced over 32 tons of milk over 365 days, over a ton of fat and almost a ton of protein. Now, obviously, diet has a huge impact inside in this, but you can see the sky really is the limit when it comes to performance. If we look at chickens, for example, and I'm not advocating this, by the way, because there are issues within the poultry industry where they bred for these animals really, really fast, and it had negative consequences. And that's a little bit like what I just talked about earlier, is that we need to be sure that when we're breeding for something, that we're not breeding in the wrong direction. But what I'm showing you here on the top line is chickens that were born in, or they're the equivalent of the genetics from 1957. And below that are the genetics equivalent from the year 2001. And that's their ages on the bottom. Now, you don't need me to show you or to tell you, look at the difference in the breast weight of those animals. Phenomenal difference between them, because they bred for these larger, meatier breasts. And over that 60-year period, you can see a phenomenal difference. Here's another example, exactly the same thing. Chickens from the 1950 at 68 days of age, and from 2008 at 47 days of age. So massive differences. But again, as I said, their breeding policy in hindsight was not the best. They aggressively bred for 1 to 2 traits, and that had negative consequences for other traits, such as leg strength and cardio, the heart as well. So how are we able to do what we're able to do in Ireland? And to me, there's a few main points. Obviously, the Teagasc research is a huge component of this, but it's largely driven by this database. We have a national database, and there's not many countries in the world that can boast about having a national database, especially one that has both dairy and beef and sheep inside in it. And this is the Irish Cattle Breeding Federation database, the ICBF. Okay. Look at this in the middle, and you can see all the data from all the other service providers, the AI companies, that's the artificial insemination companies, they do all the breeding, milk recording, the herd books where the data is recorded about the parents and the grandparents and the great-grandparents of the animals, the slaughter factories down the bottom, and so on. A few key points to take from this is look at the arrows. They're not one way, and this is key. There's arrows from the AI companies, the data is flowing into the ICBF database, but there's also an arrow flowing out of the ICBF database into the individual service providers. So providing that information that enables these different entities to make better decisions. And you can see Teagasc then on the top right from a research perspective, but also on the bottom from an advisory perspective. Just to give you a quick flavor of the data that's going into that database, there's millions and millions of data points going into that database on an annual basis. So 2.4 million birth records, almost 1 million DNA records going into that database every single year. And without that, we wouldn't be able to achieve what I'm going to show you over the next few slides. This is pivotal to that, but also a huge and massive resource available for non-genetic strategies to improve the environmental footprint of agriculture. The next few slides, I'm just going to go into the breeding, what we call the breeding goal of dairy, beef, and sheep. So a breeding goal would be like a mission statement of any company or a mission statement of a farm, whatever. What is your mission? A lot of people from a farming perspective is, they might say, my mission is to make money. And that's probably what we would have said maybe 10 years ago in dairying and beef. It's more profit for the farmer. But now we've changed our breeding goal to be more sustainable profitability with due diligence and stewardship of the environment and animal well-being. Subtle changes, but huge implications. So what I'm showing you here is our dairy EBI, our dairy breeding goal, which is called our EBI, our Economic Breeding Index. And each vertical line represents a year. The blue is the emphasis on milk production. So you can see prior to the year 2000, we had 100% emphasis on milk production. We were like the poultry industry, really. We were aggressively selecting for milk production. Now, like the poultry industry, we were going backwards then on traits like reproduction. So to try to arrest that deterioration, we included around 30 to 40% emphasis on fertility traits, reproduction and survival and longevity within that breeding goal back in the year 2000 and 2004. Every year we will sit down, Teagasc and the ICBF and industry, and we will say, well, what are the next big things that are coming down the line that we need to be cognizant of? So beef merit, calving performance, animal welfare, hugely important. Maintenance, so the size of the animal. We want animals that produce a lot of valuable product, and by product I mean both dairy and beef, but do it without having to eat as much so that they reduce the environmental footprint. Then animal health obviously is hugely important, and management. So the question I would pose, or the question you can pose to me, is what should be there in the year 2021 or 2022? And arguably there should be traits associated with the environmental footprint of dairying. So that's the one from dairy. I'm not going to go through it in any great detail. I'm just going to flash up these slides just to show you that everybody kind of talks about, a lot of people would say, oh, dairy is put up at the pedestal, it's driving on brilliant breeding gold, they know exactly what they're doing. Not true. We're doing the same in beef and in sheep. So this is exactly the same thing. We have two breeding goals in beef. We have one to produce animals for slaughter or for harvesting, and we have a second one to produce cows that have good milk, good longevity, and good environmental footprint. Again, look at the complexity of these indexes. This is just showing the relative emphasis on the traits. So we can see that in the terminal index, is the one to produce these beefy animals. Half of the emphasis is on carcass. That's what the farmer makes money when he sells it. But half of the emphasis is actually on the cost of production. So you have a dual objective here. You're trying to increase the revenue and reduce the cost. You can also see inside our feed intake. So around 20% of the emphasis on this index is on feed intake, and feed intake is strongly associated with methane. On average, and we'll talk about this a bit later, on average, the more an animal eats, the more methane it will produce on a daily basis. So that's the one for beef. Exactly the same thing for sheep. We're not going to go through it in any great detail, just to show you the complexity of breeding that exists. So there are many different traits within each of the breeding goals of dairy, beef, and sheep. And as I said, we sit down every year and we say, well, what are the new traits coming down the line? So calf vitality is going to become a big one going into the future, and product quality, and also environmental footprint. So if you looked back, and I went through them pretty fast, but if you looked at the names of those traits within the index, you wouldn't have seen any mention of environment. You wouldn't have seen nitrogen, or you wouldn't have seen methane or anything like that. But they are intrinsically inside of it. And what I'm showing you here, this is just dairy. I can show you very similar graphs for beef and sheep, albeit not to the same extent. This blue line here, so across the bottom is the year of first calving. This is a good metric to see how good your herd is improving year on year. And on the vertical axis is profit per lactation for the farmer. The blue line here is this breeding index. That's that first graph I showed you from the dairying perspective. So this is profit, EBI, increasing year on year. Look at this, the rate at which it's going from, it was started off pretty slow. Now with the new technologies that we have, like Gene Ireland and this DNA, this what we call genomic selection, is increasing that rapidly. We are doing it through an improvement in fertility. That's the green line. So our cows are getting more and more fertile. And you ask any farmer, well, is his fertility as good today as it was yesterday or last year? He'd say, yeah, maybe. But if you ask him, is his fertility as good today as what it was 10 years ago, the vast majority of farmers will say yes. And the vast majority of them will say was probably through breeding, because I'm feeding my cows the same. Exactly the same for milk production. Our profit from milk production is improving. So again, goes back to what I said from the beef. We are increasing the revenue through milk, because that's what the farmer gets paid for, but we're also reducing the costs. So we're improving the fertility. Now, Lawrence Chalou has done some work on this based on research in Teagasc, and what he has clearly shown is that from this strategy of just breeding, without any direct emphasis on methane or anything like that, we are improving the carbon footprint of our animals. In fact, over that 20-year period, we have improved our carbon efficiency per kilogram of output by 14%. Incidentally, we've also improved the efficiency by which these animals use their nitrogen. So it's a real benefit for the environment. But the great thing about it, it goes back to my MAC curve part, is that farmers are actually making more money as well on top of this. So today, the cows on average are 320 euros more profitable. This is in real terms, so you've accounted for inflation, than the cows of 20 years ago. And they're more carbon efficient. So win-win. But we're not happy with that. This is a bit of a complicated graph, so we'll go through it slowly. What we have developed is what we call a carbon index. So the EBI, the economic breeding index, was putting values on all of these traits for their contribution to profit. So Lawrence Chalou has done exactly the same thing, except he's actually put a value on each of those traits for their contribution to carbon. So if the animal weighs more or eats more, then it should produce, all else being equal, it should produce a higher amount of carbon. If it's more fertile, if it can calve earlier in the calving season, it can have more grass in the diet, which is more carbon efficient. So that would reduce the carbon efficiency. Okay. What I'm showing you here is these are all the bulls that are available in Ireland. There's around 4,000 of these bulls available to dairy farmers in Ireland. On the bottom is this economic breeding index, or this EBI that we talked about for the last few slides. That's what farmers are currently using. On the vertical axis is this new potential index, which is based not on economics, but on carbon output. So as I said, every one of these is a dot. What you can see, two things I want you to take from this line is that it's going down. So as you increase EBI, as profit per lactation increases, or as the breeding strategy of farmers, as they keep going the way that they are actually reducing the carbon footprint on a per cow basis. This is really, really good. This is a really good, it's probably called a correlation, is the strength of that relationship. It's a really strong relationship, okay? That's the first point. The second point is I've colored them differently per breeds, and look, there's not that much of a difference in the breeds. There are some really good of these, what we call Holstein animals, but there are also some good other breeds like Norwegian Reds and Friesians. But also you go to the other side of it, there's some bad ones there as well. And this is what breeding is trying to do, is trying to identify the good animals and the bad animals. The second point I want you to make, and I'll come back to this, the second point I want you to take is there's variability. So for the same EBI of 100, look at the variability that exists in their carbon output. And that's what we're trying to do for the next stage of research. If you actually take this graph, what this means is just more or less what I talked about a second ago, was for every 10 euro increase in EBI, we've calculated that it will reduce the carbon dioxide output of around 62 kilograms per lactation.
Donagh, we have a question here relating to that graph you've just shown there. The question is, how would EBI versus carbon index graph look if relative carbon was presented per kilograms of milk solid produced rather than per lactation?
It would still be favorable. Actually, it would probably be pretty similar, Mark, because what the EBI is doing, it'd probably even be stronger. What the EBI is doing is increasing your milk solids production on a per lifetime basis. And this is really important. It's on a per lifetime basis, and it's simultaneously reducing your carbon. So it would strengthen it and probably make it more advantageous. A really important point here is that people talk about a metric, be it carbon or feed intake or profit per lactation. But you can have a cow who makes a lot of profit in one lactation, but then she is culled or she dies. So she didn't make a huge amount of profit over her entire lifetime. And we need to move to talking about per lifetime. So for those of you that don't know, it takes around 2 years for a female bovine to produce a calf. So essentially for the first 2 years, they're doing nothing other than eating and producing methane. And what you want to do is you want to dilute that over as many lactations, productive lactations, as possible. So that's what EBI is doing, Mark. It's increasing milk solids output per lactation, but also doing it for more lactations and simultaneously reducing the carbon footprint of that. So it would strengthen it and make it better. Yeah, great question.
Thank you.
Exactly the same thing for the beef. Look, a lot less data points here because we're only starting to really get into this from the beef perspective. This is research funded by the Department of Agriculture through Green Breed. What I'm showing you here is the index of animals. This is remember I talked about this terminal index in beef. So higher is good because this makes more profit for the farmer. And on the vertical axis is the methane. Look at the lines going exactly, not as strong, but it's going exactly the same way down. More profitable animals produce less methane per day. Okay. And Mark, going back to that previous comment, on a methane per kilogram of feed intake, it doesn't actually change at the moment. And this is what the next piece of research is about. Now, it's very preliminary data, but it is reducing methane per kilogram, or daily methane output, but it is not affecting methane per kilogram of dry matter intake. But if you look at it from a terminal index perspective, every 10 euro increase in the index value will reduce methane. So that's the one for, firstly for dairy, then for beef, and then for sheep. And this is even more in its infancy in the sheep. This is work that's been undertaken by Noreen McHugh in Athenry with sheep in conjunction with Sheep Ireland. And we have a system in beef and in sheep where we rate the animals into 5 stars and 1 stars and 2 stars, just like hotels. So you always want your 5-star hotel, like you want your 5-star ram or like you want your 5-star bull. And when Noreen has these animals that are 5-star in genetic merit and 1 star, she's comparing them for performance, for growth, for feed intake, but also for methane. So when she has looked at it, the 5-star animals are producing, you can see here, 7.87 grams of methane per day, while the 1-star animals are producing more, 8.5 kilograms per day. So again, very preliminary, very small data set to start with. I've done no statistics or anything like that because it's just a look-see at the moment, but it's in the right direction. And it's how we would expect it to be. This is also per day. So when you can add this together with longer lifetime and shorter age at slaughter, then you're actually having a way lower environmental footprint on the whole farm level, which is key. And Mark, maybe we can talk about this one in a second, but I would pose to the audience, well, what's missing? These are what I think is missing from our breeding goal. Product quality, milk and meat. Actually, on the 24th of September with Meat Technology Ireland, we launched the first ever national multi-breed genomic evaluations for meat tenderness in beef cattle. Okay. Feed intake and efficiency. Yes, it's in there from a beef perspective, but I think there's a lot more we can do from that perspective, but also in dairy and sheep. Animal health and well-being, you would have seen it in the dairy index. Also calving performance and lambing performance is in there from a beef and sheep perspective. I think there's a lot more we can do about it. Improving the health status and the animal well-being status of our animals. And then in red, I've highlighted environmental footprint, which I'll talk about for the next few slides. And then of course, question mark, because this is a never ending game. We're always trying to look at what's coming down the line and try to address it before it happens. So any animal that is if we select a male animal for breeding today, it's really around 4 to 5 years before his daughters will actually start performing. So we're trying to guess what are going to be the big issues in 4 to 5 years' time. So just finishing off then, can we do better? As I said, we're always challenging ourselves, can we do better? So on the bottom axis here, I have milk yield, if it was dairy cow, or growth rate, if it was a beef or a sheep. And on the vertical axis is meat production, methane production. What we can see, and this would be typical enough, I just made up this graph, is that for higher the milk, the faster growing animals produce more methane per day because they're eating a lot more. But just let's look at this one. If you had an animal yielding 20 kilograms of milk, one of them is here, and one animal is here. They're both yielding the same growth rate or same milk yield, whatever, it doesn't make a difference. But look at the difference in methane. Okay, so for the same output, there's a doubling almost of the difference in methane. And as breeders, what we're trying to do is to identify these animals down here. The productive animals, they have to be productive, but also have a lower environmental footprint. The question is, as I said, I just made up this graph, so I don't know what this variability actually is. And is it worth chasing? So I can guarantee you there is variability. We have seen it, but is it worth actually putting a huge amount of money into developing a breeding program to exploit this variability? And we don't know the answer to that one yet. So to do that, I'm almost finished. We have bought the only 2 systems in Ireland to measure methane outdoors. You can Google VistaMilk and methane, and you'll see a YouTube video about how we actually do it in dairy cows. This is in the ICBF in Tully, funded through the likes of Greenbreed and the Department of Agriculture. This is a beef animal inside measuring his methane, and this is a sheep inside in what we call a portable accumulation chamber, also measuring the methane. Now, if we want to breed for something, there's 3 prerequisites that the trait needs to fulfill. So we're not going to breed for things like tail length or eye color, right? Because are they important? Well, some might argue that they are important, but they're not really important. Methane is important. 5 years ago, we probably would have said, no, methane's not important. Things haven't changed, it's just our knowledge of it has changed. So now we're saying it certainly is going to be important in the next 5 to 20 years. Okay, so methane or any environment, nitrate use efficiency, whatever, is important. 2, is there genetic variability there? So if you had cows or sheep in the same field doing exactly the same thing of the same age, is there differences in their nitrogen use efficiency or methane? There is. We just don't know how large is that variability yet. And then thirdly, and more importantly, is there data from which we can identify good bulls or rams or cows or ewes that are good for environmental footprint and bad for environmental footprint? And that's the real difficult part, is this data availability. And the technology we are trialing at the moment is this green feed system, which you can just see the cow comes into this kind of a mobile system. They get what we call concentrates, which would be the equivalent of sweets from a cow's perspective. So they really like to go in there and have a munch around. And like ourselves, if we're eating our dinner, we're breathing through our nose the whole time. And this machine is capturing the methane that's coming out through their nose. A lot of people actually think that methane comes out the other side of the cow. Most of the methane will come out through its nose. And it's the same thing from a sheep perspective. So you can capture then how much methane each cow is producing, and that'll give us an idea of how much variability exists. The last one there, just before I finish up then, is another technology which we're investigating, is called infrared spectroscopy. Joe, if you go to the doctor and you're a bit sick, a lot of the time they might take a urine sample of you, and they have this kind of a piece of paper, and they'll run the urine over it, and they look for a color change. So a lot of what happens inside in your body comes out of you in one form or another. And it's kind of similar enough in cows. So what's ever happening inside in the cow, be it inside in her stomach or physiologically, or if she's sick, a lot of that you'll see it in the milk. And because in Ireland we milk our cows twice per day, you get access to this biological sample, this really rich, potentially rich biological sample twice a day, because it's part of daily routine. So the question we are posing is all this methane produced in the rumen, does it materialize in the milk? We know we can predict a lot of things inside the milk. So there's lots of stuff, molecules inside the milk, and they vibrate and things like that. And what you do is we shine light on that milk sample. This is undertaken across the world. All the cows that are milk recorded across the world, as well as bulk tank samples, go through this process. Light is shone within there, and it produces a kind of a spectrum of where the milk or where the light is being absorbed. This is used around the world to predict fat, protein, and lactose. So any dairy farmers in the audience, you get your fat, protein, and lactose back from either your milk recording or from your bulk tanks. This is the procedure that's being used. So we know that we can use it to actually predict other things like fatty acid concentrations. But what we're asking Sinead McParland's work is, can we use it to predict methane? The biological hypothesis would say yes, but and the very preliminary evidence would also suggest yes. The beauty of this approach, as I said, it's already been done. Farmers are paying for this milk recording system. So as well as getting your fat, protein, and lactose, you could get things like your energy balance and your methane production, and enables us then to breed for it. So just the take-home messages, Mark. I don't think there's anybody that's going to deny that sustainability is key. And I think when we talk about sustainability, it's really important that we're cognizant that economic sustainability is also a metric of sustainability. And that's why breeding is a great vehicle to improve the sustainability of the sector, because these indexes that I talked about, they're all profit-based. So if we can keep those improving, the farmers make more money, and if we can introduce new environmental traits into that, we can simultaneously improve the economic sustainability of the sector, but also the social sustainability of the sector. While people would look at a lot of these things as challenges across the entire industry, I look at these as opportunities. We had huge issues 15 years ago to 20 years ago with fertility in Irish dairy cows, and we've just turned it around. It didn't take us all that long. It took us 10 to 15 years to turn that around, and now we have one of the most fertile herds in the world. And the other thing, of course, this is just the arrogance of me coming out as a geneticist, is that breeding is cumulative and permanent. So it's a brilliant strategy to improve things year on year. But as I said, also, it can also be to our detriment. We can disimprove things year on year if we're not very, very careful. And also, it's not slow. As I said, I was taught in college that breeding is too slow. We have clearly shown, we have the very strong evidence to show that it is not slow whatsoever. So that's it, Mark. Hopefully it was some way entertaining and enlightening. So I'll take any questions there now.
Right, Donna, thanks very much. Really excellent presentation, and I think you've very easily broken down some quite complex areas into understandable language there. So thanks for that. We're getting lots and lots of questions coming through here, so obviously you've stimulated a lot of interest. But just before we go to the questions, Donagh, I'm aware that a lot of your work is involved in the whole area of genomics, and it's an area that is relatively new. But maybe you could just explain to us what's happening there, or how that's actually affecting the whole, I suppose, the speed of which animal breeding is going.
Yeah, so genomics is really just a fancy word for genetics, and we've actually been using genomics for the past few centuries. We just didn't know about it. So genomics, like DNA, is we look at our DNA, right? So Mark, I've met you, you're a pretty tall guy. So I actually can predict that your DNA, you are carrying DNA for tall genes, okay? Because you are tall. But I haven't measured your genes. Now, if you have one kid and one of those kids is tall, I get a better reflection of the fact that, yeah, okay, the fact that you've transmitted on your half of your genes and your kid is tall, I'm now more confident that you are carrying tall genes. Now, if you're like a bull, Mark, and you had 10,000 kids and all 10,000 of them are tall, then I'm 100% confident that you're carrying tall genes, right? So all this genomic or this DNA technology is doing is not waiting for you to have 10,000 kids, Mark, but it's looking at your hair at 1 day of age, because there's DNA inside in your hair. So we take a hair sample or blood sample from a sheep or a cow, we look directly at its DNA, and then we get a prediction of its progeny performance. So it's essentially putting our traditional approaches on speed. So we're not waiting for this 6 to 7 to 8 years for this bull or this ram to have many, many progeny to get an idea of what his DNA is like. We're straight away going in, looking at his DNA. So the DNA that you were born with, Mark, is the DNA that you're going to die with. And the DNA at the end of your nose is the same as the DNA at the end of your toes. So we can take any one of your samples and get a good reflection of your performance, but also your progeny and your grandprogeny's performance.
That's excellent explanation. It's been a while since I've been compared to a bull, Donagh. So look, I failed to introduce our colleague Pat Murphy at the start. Pat is our head of environment knowledge transfer. Is going to help us out with the questions. Pat, there's lots of interesting questions coming through here this morning.
Yeah, I suppose one theme, are there any particular traits within the EBI index that show correlation with methane output? And I suppose there's another question in relation to identification of traits for, or of, I suppose, DNA that links to methane levels of output. Is there differentiation and is there heritability there? There are kind of two themes that are appearing.
Yeah, great questions. So the first question was about relationships between traits and let's call it environment, right? Bigger scheme. Yes, there is relationships between traits. On average, the more a cow produces, the faster an animal grows, the more it will eat, and therefore the more methane it will produce per day, right? That's fact. But it's on average. And what I showed you in my second last graph was that scatter that exists. So there is a relationship, but as geneticists, what we try to do is break that relationship and look for animals that are high performance and profitable, but also have a lower environmental footprint. One that people do forget is the issue of longevity. So what I said, remember, was you're trying to dilute that period when the female is doing nothing because she's too young. She hasn't hit puberty. All she's doing is producing methane and excreting nitrogen, and you want to dilute that over a longer time period. The third point, from an Irish perspective, we know if we, depending on the analysis that you do, but this thing called complete life cycle analysis, which accounts for everything, like it accounts for how the feed was produced. Grass-based systems have a low environmental footprint. So if we can maximize the amount of grass in our dairy cows' diet, we will have a lower environmental footprint for the entire sector. So by having good fertility and getting our cows to calve earlier at grass, maximize amount of grass in the diet, we can reduce the environmental footprint. Your second question was on the heritability of methane production. So heritability is a statistic that we use, is technical, and it tells you how much of the variability is due to genetics. So you go into a field of cows and they're all fed the same because they're all in the same paddock, but there's differences in milk yield. Why? Well, probably because of genetics. So 35% of that difference is actually due to genetics. 50% of the difference in the protein composition is due to genetics. 35% of their differences in their weights. You know, you have big cows, you have small cows, is due to genetics. Mark, go back to you. 80% of the differences in height in humans is genetic. That's what heritability means. The indications, no data from Ireland yet, because we're just collecting the data. Indications are that 17% of the differences in methane production are genetic. Okay. And your point, it was inside that was the pieces of DNA associated with methane. I come from a school of thought as breeders where we're not actually interested in the pieces of DNA that causes these differences. People have looked at this over the past 30 years. They failed to find anything really associated with any of these traits. We look at the entire DNA complement of the animal. So it's not looking for the genes that are associated with height and mark. We're looking for the entire DNA profile that's associated with height. And that's the safest bet. If you go after individual genes, you don't know what the repercussions actually are for other traits.
Donagh, we have a few questions, Donagh, in relation to animal health, particularly in relation to disease. You know, are there possibilities there for us to breed animals that are resistant to TB, for example? Or we know that there's a growing issues with antimicrobial resistance and wormer resistance. You know, where do you see the potential there?
Yeah, so I don't think, with the exception of a few genes or a few traits that are yes, kind of no, or yes or no's, I don't think we will ever eradicate any disease through breeding. Right now, we did launch, again funded by the Department of Agriculture, we did launch national genetic evaluations for TB last year. Right, so it goes back to my 3 points, Mark. Is it important? It certainly is important. It costs us 80 million euros a year as an industry, TB does. 2, is there genetic variability? This was Pat's question. 18% of the differences or the susceptibility to TB is genetic. And 3, have we data? And that's the one that we always trip up on. Have we data? Every farmer in Ireland, beef and dairy, is subjected to an annual TB test. So we had the data. We call a lot of these data, the fancy word for them is called phenotypes. But I call these ones phenotypes because they're free. They were already in the Department of Agriculture database. So it enabled us to do a national genetic evaluation and the farmers didn't have to do anything. So now the farmers can go on and they can look at bulls who are carrying more susceptible or less susceptible genes to tuberculosis. Same thing, Mark, then about the rumen fluke and the liver fluke. We actually launched national genetic evaluations for liver fluke at the same time, the parasite of the liver. Why? Is it important? Yes, it certainly is important. 2, is there genetic variability? Yes, around 2 to 3% of the susceptibility is genetic. 3, the one we always trip up on, do we have data? Well, actually we do, because every single carcass that is slaughtered in a slaughtering plant in Ireland is inspected for liver damage. So we actually had a phenotype again. Now, goes on to your new traits, Mark, and I know I'm talking away here, mastitis. Is it important? Certainly is. And let's do mastitis and lameness together. Are they important? Really important. 2, is there genetic variability? Yes, around 3% of susceptibility to mastitis and lameness is genetic. 3, the one we trip up on, have we data? And this is where we're falling down here. We don't have a huge amount of data. Dairy farmers, beef farmers, maybe to a lesser extent, do record lameness and mastitis. They record it, especially when they treat it, because it goes into the dump line. The problem is they put it at the end of the milking, on the whiteboard or the blackboard at the end of the milking parlour, and it never makes its way into the ICBF database.
Are they not relatively small percentages, though, Donagh, the 1 to 2% you talk about that's related to genetics? Just to challenge you on that.
Brilliant question, Mark. And again, this is what I was taught in college. This trait, there's only a small amount of it is genetic, and therefore you can't improve it. We have quite clearly shown that is complete and utter rubbish. So fertility, you ask any dairy farmer, Pat will tell you, fertility in the Irish dairy herd has improved dramatically over the past 15 to 20 years, predominantly from breeding. How much of that is genetic? Any idea? 2 to 3%, Mark.
Right.
So we have done, as geneticists, hands up, we did a great job in absolutely destroying fertility prior to the year 2000. And now we've done a huge, brilliant job in improving fertility, even though it was only 2 to 3% genetic.
So
we can do
cumulative effect.
Yeah, the difference, Mark, was that post BSc we had to record birth dates, and therefore we had calving dates, and therefore by extension we had calving intervals and survival. So we had the data again freely available to us. We don't have it on the health traits, and that's a real bugbear of mine, is that we need access to this health data.
There's a question here, just says, great presentation. Just wondering, the more we harmonize traits for commercial gain, do we reduce the natural genetic diversity in a given species? And could this pose a longer term threat to population resistance for future threats such as new diseases?
So quickly, Pat, no, it doesn't. It actually does the opposite. But I want to answer the second part first, which is completely correct. If you reduce diversity, you reduce the ability to deal with these external perturbations, be it new diseases that come in with climate change, because we're going to get probably new exotic diseases coming in that our populations are naive to, but also our ability to change the herd or the flock towards lower environmental footprint. So if you had one trait and it was milk production, I can guarantee you, well, we have evidence of this, that it will reduce the diversity really, really fast, because you'll have 1 or 2 families that are really, really good at milk production. Now, if you widen that to have milk production and fertility, you actually widen your genetic pool. So the more and more traits you include, you actually, because it's like being a master of all. You have to, you can't get these guys who are masters of all. So you have to keep identifying these new families and interbreeding them to actually improve genetic gain. Another real important point is that it's really hard to get rid of genetic diversity. And I can show you experiments from the US, from Iowa, where they have started with 6 ears of corn 116 years ago. And they only use those 6 years of corn. And they can still make massive genetic gain. Halfway through the experiment, they changed their breeding goal, and they actually also had massive diversity within there to react to a particular change in demand. So don't be overly worried about diversity. Another point before I stop, I know I'm rambling, is that farmers really have little to no input in diversity. It's driven by the top of the breeding pyramid, which are the breeders and the AI stations. So the farmers who use AI, they might think that they're picking their bulls, but they're only picking the bulls that are made available to the AI stations. And we have breeding programs that Teagasc are involved in trying to maintain the genetic diversity across generations. So really, really important, but I would say, Pat, don't be worried about it.
Okay. And another question there in relation to the potential impacts and potential opportunities in relation to the quality of the food that we produce. Are there opportunities there, or are there threats in relation to it from the breeding policy?
So like I said, the opposite to opportunities is threats. So I would argue there is massive opportunities. And I think, like, if you think about the fact that we export, 95% of our beef and our dairy, we're the 5th largest exporter of beef, we're the 10th largest exporter of dairy in the world. We have this selling point, this unique selling point of grass-based, welfare-friendly, etc. But people are catching up to us, and they're catching on to us as well. So we need to look for this new point of differentiation. And I would argue it's going to be in the nutritive value of our dairy and our meat. As I said, with Meat Technology Ireland, we launched the first global index in the world, breeding for animals who have superior tenderness, juiciness, and flavor. Can we bring that to vitamin E, other micronutrients? I would argue we can. I have yet for somebody to tell me a trait that is not under genetic control. Goes back to Mark's point. Even if it's only 1% under genetic control, we can do something with it. Same for milk. Right? We got things like omega-3. We see a lot of these products now, omega-3 for your for brain development in chickens. Another good one is A2 milk. People might have heard about A1, A2 milk. Very tentative links with human health, right? And we can argue for this for a few days as well. That is just affected by one DNA variant. So the DNA variant of the cow will determine whether she produces the A1 milk, which is, some would speculate has negative or adverse human health consequences, or A2 milk. So we could change like that the national herd to producing A2 milk. I think it's something that we really need to start focusing on.
Okay. Question there, just as a great presentation on a complex subject. Dairy breeding seems to have left beef merit of male calves behind. Is this being addressed?
Firstly, acknowledge, yes, it has under the current system of beef production, which is your fillets and your steaks, etc. Is it being addressed? Yes. But I think we might have to look at this in two ways. We have to probably look at how we define beef at the moment. If we look at the price trends, right, these high value, the stuff when you go into the butchers and you see the steaks in front of you, they haven't really changed massively in price over the past 10 years. While the more processed meat, the minces, etc., are increasing. And we're probably going to see a lot more of this actually through COVID as well for these ready-made meals. So these excellent quality animals that we're used to for the past 20 years, the differential is actually reducing relative to the lower quality ones. Now, the second point is the environmental consequences. So if we can get animals that are slaughtered at a younger age, albeit maybe not to the ideal confirmation score that we wanted heretofore, they could actually A, be more profitable because we're not feeding them for longer, farmers are not feeding them for longer, and B, they could actually be more environmentally efficient. Okay, so that's the first point. The second one then is, are we addressing it? We have a new index, which I didn't present there, which is called Dairy Beef Index. We launched that around 2 years ago, which is for the identification of beef bulls for use on dairy cows that will have minimal animal welfare consequences, so it won't increase calving difficulty, but will also have good growthy animals that the factories currently want, the meat factories currently want. So that's trying to negate the impact of the dairy herd reducing in size, and confirmation score in particular is the one that we're really seeing as an issue from the dairy.
Donagh, we have a question here in relation to the health traits. It says lifetime performance requiring 5.5 lactations. Are dairy health traits going to be strong enough to prevent high vet labor issues in managing older herd profiles? I think that's a really good question in terms of the costs of cesareans and so forth.
Yeah, I don't know if that person has heard me going on about that. This is my new bet one as well, is that I think my saying is that health is going to be the new fertility, right? So our cows on average, dairy cows are living for around 3.2 lactations, right? So that's around 5.5 years, let's say. We want them to live for another 2 lactations. So we want them to live from 5.5 years to 7.5 years. Now, humans in Ireland live for 78 years. So a cow year is the equivalent of around 12 human years. And we're asking cows to live for 2 more years. So essentially, Mark and Pat, I'm asking you guys to live for another 24 years. So what's going to catch you? It's going to be your health. You go into the hospitals today. I'm not the people in the hospital. It's all old geezers are inside in the hospitals, right? And cows are going to be the same. As our cows get older, health is going to become more of an issue. Legs, from a dairy perspective, because they're walking for 2 more years, all that distance. Feet and legs are going to be more important. The confirmation of the udder is going to become more and more important because they're milking for 2 more years. And I think we're going to hit a big problem in the next 5 to 7 to 10 years unless we seriously address these health things. But I always throw it back to the farmers, is that I can't tell you what is a good bull or what is a bad bull without the data, without the mastitis data and the lameness data. Same with sheep, right? Lameness, big issue in sheep, right? It is under genetic control. We've clearly shown that. We launched genetic evaluations for lameness in sheep around 4 years ago on your Brian's work, right? So there's massive potential, but it's reliant on the data. But it's going to become more and more important, health definitely into the future, as our fertility improves and we enables our cows to live for longer. Real important point, Mark. I
suppose a more general question, Donagh, is just in relation to the breeding and selecting for methane or reduced methane animals. I mean, are there any potential negative effects or outcomes from that?
I'm sure there is. I'll just give you an example. So methane is produced from the digestion of a product from grass. So an easy way to probably reduce methane is to get the stuff to go through the cow as fast as possible with no bugs inside it that digest it. So all essentially the stuff is, the grass is going in the cow's mouth, coming out its bum, and it's producing nothing for the cow, right? Because the cow didn't digest it. So well, we don't know, but my hypothesis could be is that if we reduce the methane output per kilogram of intake, the cows aren't digesting the grass as well as what they used to. So what we might want to do, and we don't know the answer to this, right? But what we might want to do is to get the cow to eat less, right? Grass. It has to have the capacity to eat grass, but to eat less grass, but to digest it better. So to produce more per kilogram of what it eats, but to eat less kilograms and therefore produce less per day. And a little bit back to Pat's point about the metric, I was talking about total carbon output, and Pat's first question, your question was, well, what about methane output per kilogram of milk solids? And I'm still sitting on the fence. We need to look at these metrics as what is the best metric to use here. So yeah, I think undoubtedly, Pat, everything is negative. There's a reason why these cows produce methane. Ruminants produce methane. There's a reason why they do it. Like evolution over the past few millennia have enabled this to happen. So.
Question there, how much are stock bulls holding back replacement breeding for both dairy and beef?
They are holding it back, Pat. The extent of what they're holding it back, it'll be difficult enough to quantify, but don't shoot them completely. Like, I know I'll be shot for probably saying this, but stock bulls, the vast majority of the stock bulls are AI bulls in themselves. The sires of those stock bulls are AI bulls. So the impact of the AI industry, it does make its way down to the commercial production, either via AI directly or through a natural mating bull. What the natural mating bull or the stock bull does is just slows down the rate of genetic gain. So yes, stock bulls, they do reduce the rate of genetic gain. However, we have to, Pat, be cognizant, especially in the beef herds, about what the vast majority of farmers are. I'm a beef farmer myself. I'm here talking to you guys. I'm not out heat detecting my cows, right? So, and I have a small herd, right? So they're not bulling together. So like, I do use AI, but like stock bulls, they have a role to play. I'm probably going to get destroyed on Twitter for saying that, but they do. We can't always go with the best science, right? The science is telling us to slowing it down, but we have to be cognizant of the demographics that are actually out there as well.
I suppose if we finish, some of the questions are alluding to thoughts of Mark having 10,000 children. Is
I'm laughing here. Harold Kingston is starting a new hashtag, Mark the Bull here. So don't know what you start.
Next time, Mark, I'll use a horse analogy, I think.
Yeah, very good. Look, we're out of time, unfortunately, and I know we could so easily go on for another hour to discuss this topic, because it is fascinating. And as I said earlier, Donagh, you've really done a great job in pulling together a very complex area. So we appreciate that.
Mark, I think there's a number of questions there relating to methane, and I think there's a merit in one of or two of our other colleagues like Sinead Waters coming on and doing a session specifically on methane emissions. So we'll organise that into the future.
Yeah, no, that's a good point. Huge interest from our audience, and a lot of congratulations to just pass that on to you, Donagh. So thank you again, and Pat, thanks for your help today with the questions. I want to thank our production team, Andy Boland and Yvonne Maher, and I also want to tell you about next week's presentation. We'll be hearing from Dr. Michelle McCormick from the Agricultural Catchments Programme, and she'll be talking about the economics of catchment management, linking science and farmer behaviour in the Agricultural Catchments Programme. So with that, I want to thank you for tuning in today, and we do hope to see you next Friday, and take care of yourselves and stay safe. So thanks a lot.
You've been listening to the podcast version of the Teagasc Signpost series, the weekly webinar that promotes and examines sustainability in Irish farming. Don't forget to join us live every Friday morning for our latest webinar. For more, visit teagasc.ie. And you can also rate, review, and subscribe to the Signpost series on Apple Podcasts, Spotify, or wherever you get your podcasts from. I'm Mark Gibson, and thanks for listening.